Okay, I'm going to dive down just a little bit further now into the getting to smaller and smaller scales before we come back up. But I'm going to give you a little example of some new things that we've been discovering out at the lab. And this has to do with reactivity of supercritical CO2 with different materials. And this is something that's really only come to light in the last year and a half. So we and a lot of others have been looking at this sort of conventional picture. That is, if you're talking about reactions, chemical reactions in the subsurface or in pipelines, it's really about CO2 dissolving in water. And so this is a figure where we're looking at what's the concentration change, and I'm referencing it, so a point here at depth. So what is the solubility of CO2 in water as I change my depth in my reservoir? So as I go deeper, temperature is going up because I have a geothermal gradient, and pressure is going up. As temperature goes up, CO2 solubility in water is this thing called retrograde solubility. So the solubility goes down as temperature goes up, but pressure is increasing. So those two effects counterbalance each other. So what you see is that if we look at different depths, reservoir depths, CO2 solubility in water is basically constant. It doesn't change very much. Not true for water solubility in CO2. That's something that hadn't really been looked at very closely as recently as just about 18 months ago. In fact, water solubility in CO2 changes dramatically. So as we go deeper, we're talking maybe 20 times more water in the supercritical CO2 phase. So very, very big change that's occurring in supercritical CO2. When we talk about water, you've got, of course, solubility products, you've got different ions that can form in solution, you have all the standard things that we work with as chemists and geochemists. None of this applies in supercritical CO2, does it? There's no free water phase. There's no such thing as activity coefficients, solubility products. None of those constructs that we work with as chemists and geochemists work in supercritical CO2. So we're kind of back to the square one in terms of trying to figure out, okay, so then if we see something, what's driving those reactions? So the key point is, do we see something? I love these simple experiments like this, and this is one of those. So we have a pressure vessel here, and what you see is this is water, and this is liquid CO2. This is just room temperature. So it's about 700 psi. And all we did in this experiment is just put a pipeline steel that straddled the interface between those two phases, just room temperature. Sat there for just a few days. So what do you see? What you see is that in the liquid water phase, so down here, the steel surface looks pretty pristine. You know, nothing much has really happened. This is where we speaking about geochemists, geochemical modeling, this is where we've been focusing all of our attention. But look up here. Look up in the liquid CO2 phase. This is that steel coupon's corroded like crazy. That's an iron carbonate that's formed on the surface. This is just a few days at room temperature. So all the interesting chemistry is occurring up in that liquid CO2 phase where we really haven't paid much attention at all. So that's with steel. And we can get into more details about what's happening with those reactions with the CO2. We use a new technique. We use a technique called molecular dynamics to go after that. And what this is doing is letting us look at, well, okay, so how is that water, which is solvated in that CO2 phase, interacting with those steel or iron surfaces? And what these tools let us do is look at the molecular interactions on these surfaces. So what's happening is we've got water which is now hydroxylated the surface of this iron that we're sitting here. So we've got these hydroxyl groups which was formed on the surface. This is a CO2. So the CO2 is approaching, and you can see that now that water's come back out, and so it's free to go off and hydroxylate other sites on the surface of that steel. So it's a true catalytic reaction. And what you see here, of course, is iron, and this is carbonate. So it's an iron carbonate that's forming on the surface of the steel, which is exactly the corrosion product that we saw. So we use these molecular dynamics tools to examine what's happening on the surfaces of components like this. And it can get even a little more complicated if we've got CO2 that's mixed together with SO2. So this is a contaminant which comes along with a lot of combustion systems. What we see is that the SO2 is attracted to, this is a manganese atom which is on the surface of that steel, and it binds preferentially to that site, even in the presence of CO2 that you see here. So as engineers, what happens is we go back to the literature, we look at what pipeline engineers typically do when they're doing CO2 projects. They specify a high manganese steel to inhibit corrosion for CO2 projects. If you've got SO2 into the system, that's a mistake, because what happens is that SO2 is attracted to that manganese in that system. And we know that now from these calculations, and we see it in the lab too. We see that we get these manganese corrosion products with SO2 mixed into the system. So these are the details that you really have to know when you're doing these sequestration projects as engineers.